Now, in this lesson, we are going to deal with column vectors. So we have what we call column vectors. I can say now this is this lesson now start to that we have started the real vectors. So in column vector, we talk of displacement. Displacement consists of 2 points. So we can have a point moving from A to B. We are going to use the Cartesian plane to describe that. So let me draw a Cartesian plane here. So that is our x-axis, and this is our y-axis. So this is our y-axis, and this is our x-axis. I'm sure you have dealt with the Cartesian plane. So we can label 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Now, column vector. So we can have 2 points, and 2 points to represent. Let's take that point. We have a vector. I can use a different color there. We can have that vector. So we say this is vector A and B. So you have this is A and this is B. So vector A and B, we can have the position vector, the coordinates of A. We have it is 1, 2. I hope you remember how we do it. We read the coordinates x and y, and then we have B. B, the coordinates of B, we have 5 and 8. Now, since we are talking of displacement, displacement means moving something from one place to the other. So it is A is being displaced up to where we have B. We can use what we call components. Components, we say this vector can be represented by these components. So we have that and that. So this component means, so alternative route, you can move from A like that. Now you find that along the, this is along the x-axis, we have 1, 2, 3. So we have 3 units. We have, so you can see from 1 we get to 5. That is, actually there are 4 units. You add 4 units. What about along the y-axis? So let's change this to 4. We have 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. We have 5. This is 3, not 2, as you can see here. So we have 5. So when we write a column vector of AB, we can say AB, like saying is to move from A to B, is that you move 4 units along the x-axis and 5 units along the y-axis. So column vector, we describe our vector in that format, that you move 4 units along the x-axis and 5 units along the y-axis. So that is what how we represent a vector in column form. We can have another vector here. Let's say we have that other vector like that, and this vector we can label it FP Q. Now we can have the coordinates of Q of P are 5, 1. Coordinates of Q are 8 and 9. 8 and 9. No, in terms of component, we can say that we can describe the component of this vector as these are the components. So we say 1, 2, 3, 4, 5. We have 5, and we have 1, 2, 3, 4, 5, 6, 7, 8. We have 8. So vector PQ, we say PQ is equals to 5 units along the x-axis and 8 units along the x-axis. If you observe here, to get 4 and 5, we can say AB is equals to 5 minus 1 and 8 minus 3 is equals to 4. You get 4, 5. For this one, we can say PQ, we take the coordinates of Q, so it is 8 minus 5 and 9 minus 1, and that will give us this will give us 3, not 3, this is 8, 5. You get I think here we got 8, we got 3, we have 1, 2, 3, 4, 5. We have 5, but the coordinates is 5, 1. So we are talking of this is 9. So we have 9. So we change this 9 minus. We get 9 minus 5. We get 4, and 9 minus 1. We get 8. So I think this is wrong. So that is how we get the column vector. It describes the displacement. Let's do an example and see whether we have understood. We say find the sum of each of the. We say example. Find the sum of each of the following. Each of the following column vectors and illustrate their solutions graphically. And illustrate their solution graphically. So we have A is equals to 2, 3, and B is equals to 7, 1. Now, and we have B, we have C is equals to minus 4, 2, and we have, and D is equals to 5 minus 2. Now, we can use, we say that total displacement, so we can use the Cartesian plane. Let's draw the Cartesian plane here. So that is the Cartesian plane. We label our Cartesian plane, so we have 1, 2, 3, 4, 5, 6, 7, 8. We have 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that. Now, displacement, we can take A. We take A, we say it is 2, 3. So we can put our vector like this. It is 2 units along the x-axis and 3 units along the y-axis. 1, 2, 3. So that is our vector A. which we can label A. Then we have B. It is 7, 1. So we can start our vector here. You draw your vector like this. 1, 2, 3, 4, 5, 6, 7, and 1 unit. So that is our vector B. So to illustrate vector AB, now you come and say draw that. So that is our vector AB. So this is our vector A plus B. And we can prove that because we can say A plus B is equals to, our A is, let's use a different color here. We have A plus B is equals to, our A is 2, 3, as illustrated here. Then plus our B is 7, 1. We add the corresponding. 2 plus 7 is 9. 3 plus 1 is 4. Let's check our components of the vector AB. You can see along the x-axis we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So that is a component of vector B, AB, x component of vector AB, A plus B. Then along the y-axis, 1, 2, 3, 4. So this is 9 and this is 4, as we have proved that. So you can see it works. So that is how you illustrate. So you can, when you sum, you get this. When you illustrate, when you sum, you get that. When you illustrate, you get this. From there we go to the other vector C and D. We can possibly make duplicate that so that we have we retain our first one. So we have the previous one and this, now we have this. So we are supposed to sum these vectors, and so we can remove the first one. This, so that we use it here. We use the same Cartesian plane. So we come and say minus 4, 2. We can start from anywhere. Minus 4, 2 means 1, 2. Let's use this color. We have 1, 2, 3, 4. Those are 4, and 2 to the positive side. 1, 2. So this vector means it is like that. Not like that, but like that. So that we have along the x-axis it is negative 4, and along the y-axis it is positive 2. So that is a vector C. We say this is vector C. So that is vector C. Then D is 5 minus 2. So what we can combine these two vectors and say, then we since we are told C plus D, we say it is 5. 1, let's correct that. Let's put it correctly. We say 1, 2, 3, 4, 5. That is the positive direction, and Y is 1, 2. So that is our vector. So this is our vector C, and this is our vector B. So it means that our vector here is this one. And so this one is a vector A plus B. We can prove that because we can say C plus B is equal, and C plus D. Let's correct that, plus D. So we say C Okay, still not okay. We need to correct here. We are dealing with C plus D. So we say C plus D, and you can use that to indicate their vectors. So we say it is minus 4, 2. We are adding plus 5 minus 2. So you find that minus 4 plus 5, that is minus 4 plus 5, that will give you 1. And 2 plus minus 2, that will give you 0. And as you can see, our vector here, it has, you can see this vector here, it has only 1 unit along the x-axis and 0 units along the y-axis. So you can prove that. So that is how you work out that. So we get to another. So I hope you understand what are column vector. They represent displacement. Let's do another example. We do another example here. This example, it says if A is equals to 3, 2, if A is equals to 3, 2, and B is equals to 1, 4, find 3A plus 2B. Now, this one, we can say the solution to this one, we talked about scalars. So we can say 3 and 2 are scalars. So what we do is we just say 3, our vector is 3, 2, plus 2, our B is 1, 4. So this will give you what? When a scalar, you multiply each an element by the scalar. So 3 times 3 is 9, 3 times 2 is 6, plus 2 times 1 is 2, 2 times 4 is 8. Then you add the corresponding 9 plus 2, that will give you 11, and 6 plus 8, that will give you 14. So that is the sum of these two vectors. So I hope now you understand what column vectors are. From there, we go to what we call position vector. The position vector. In simple description, position vectors are those vectors that start from the origin, and the origin is 0, 0. So if you draw the Cartesian plane here, if you draw the Cartesian plane there, then you say this is, you name your Cartesian plane, you say this is 0, you have 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Now we can make a point here known as, let's put that point to be A. We can make a vector from the origin. Origin is 0, 0. Which we also call it A, the starting point 0. So we can make a vector from the origin to where we have A. The coordinates of A are 3 and 7. So we have 3 and 7. So this is a vector. So to describe OA, it is a vector from the origin, is equals to, it refers to a position vector. Numerically, we say, since we have O is 0, 0, we have A is 3, 7. So we say the displacement here is from 0 to 7. So OA, we say, is equals to 7 minus 0, and 3, not 7 minus 0, but 3, our x is 3 minus 0, this 3 minus this one, and 7 minus 0, So you get it is equals to 3, 7. So our vector OA is 3, 7. We can pick another point on the Cartesian plane and say this is our point, and this point we call it B. So we can make a vector from O to B, which we have the column vector of the coordinates of B are 9 and 4. 9 and 4. So we can say OB is a position vector because one of the point, the first starting point is the origin. Any vector starting from 0, 0 is called a position vector. And you note that before we even write for B, OA, we have said it is equals to 3, 7. So if you are given a point on the Cartesian plane and you are asked the position vector, it is the same as writing the coordinates in a column form or in a vertical form. So OB is equals to 9, 4. I don't even need to, because I know the starting point is 0, 0, and when I subtract here, it will just give me the same. So that is the position vector. Any vector starting from the origin is known as the position vector. Position vector. Now, with the position vector, let's see, we can form a vector known as OAB. Now, AB is not a position vector because it is originating from A. It is originating from A to where we have B, and we can be able to get the displacement as a column vector and say AB is equals to, we say to move. Now in vectors we say to move from A to B, it is, we can take an alternative route, AO plus OB. So instead of writing AO, that is AO plus OB, but we don't like writing it like this, so we say it is minus OA. We are moving in the negative direction, plus OB. Now this will give you, what is our O? This is OB. We can rearrange it to AOB. Check this. Minus OA. But we already have our OA is this. So this gives us 3, 7 minus, not that is OA. We want OB. OB is 9, 4. You minus OA, which is 3, 7. Now that will give us the 9 minus 3 is 6, 4 minus 7 is minus 3. And surely you can see our vector describe the same. You see components are 1, 2, 3, 4, 5, 6. Then that is a positive direction of X, negative direction of Y, 1, 2, 3. So we get, that is what is described here. So that is a position vector. That is what we call position vectors, and that is the difference between the position vector and the column vector. And this is very important in vectors because from now henceforth we will be dealing with column vectors and position vector. Even in Form 3 we will continue. So it is important that you understand the column vector and the position vector. I'm going to do for you maybe two or three examples, and then we can wind up this lesson. So we start with the lesson with an example. Okay, example. In our example, we are told draw the following position vectors on square paper. Draw the following position vectors not just position vectors. On a square paper. So if you have a graph, you can use a graph. If you have yeah, I can use a graph, but because it's just simple description of the vectors, I'll just use a grid. So we have A is equals to minus, this is minus 1, 2. We have B is equals to 2, 3. We have C is equals to 0, 4. We have D is equals to 3, 0. We have we have E is equals to 5 minus 2. We have F is equals to minus 3 minus 4, and we have G is equals to that is minus 2, 2. I think those are enough. So we can handle those ones. So I'll just use a Cartesian plane. I just draw my Cartesian plane here. So that is my this is my y, and this is my x. Now once you have that, we can label 1, 2, 3, 4, 5, 6, 7, 8, 9. We have 0, the starting point. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think we need, let me change that. Let me draw a Cartesian plane that will fit on both sides, negative and positive. So we just draw a Cartesian plane that is that will be able to cater for even the negative. We have negative, negative. Okay, so we have this is so that's our Cartesian plane. That is better like that. So this is our y, this is our x, this is 0. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 1, 2, 3, 4, 5. We have minus 1, minus 2, minus 3, minus 4, minus 1, minus 2, minus 3, minus 4, minus 5. Now we are talking of position vectors. So this means that these are vectors starting from the origin. So if we say minus 1, 2, we move to, we starting from the we move minus and 2. So that means that our vector is minus 1 and 2 in the positive, minus 1, 1, 2. So that is our vector A. That's vector. It's a vector starting from the origin. So that is our A. We come to B. B is 2 units on the this, I think this is 4. I hope that is yeah, that is 4. We come to vector B. It is 2 units. So we say it is let's use that color. It is 2 units along the x-axis. 1, 2. 3 units. 1, 2, 3. So that is our position vector AB. What does it mean? It means 2 units along the x-axis, 3 units along the y-axis. We come to the other one. It is 0, 4. So it means no displacement along the x-axis. So it will be 1, 2, 3, 4. That no, 3, so it is a vector 1 along the y-axis up to here we have 4. Sorry, we have that. So that is a vector I hope you understand that this is a vector C. 5 minus 2. 5 minus 2 can 5. So we say from here 1, 2, 3, 4, 5. And the minus 2. 1, 2. So that is our position vector E. So this is our vector E. Okay, we look at F. F is minus 3, so we move just a minute. We have 1, 2, 3, minus 3. 1, 2, 3, 4. So that is our vector F. That is our vector F, negative. And then finally, we have our G, minus 2. So we take minus 2. We take 1, 2, and the other one is positive. 1, 2. So that is our vector G. So I hope now you understand what position vector. Any vector starting from the origin is referred to as position vector, and I hope that is clear. I don't know, we look for one question for the, I think that is for the column vector. Let me check if there is a question we can do. I think we'll get one on position vector. So generally, we can say we have discussed column vector, column and position vector. Position vectors. So you can conclude and say, if you have a Cartesian plane like this one, Cartesian plane is where we have x and y coordinates, like that, and we have that our x, that is our y. A position vector, I'll demonstrate. It's any vector starting from the origin. Any vector starting from the origin. You can see that. Any vector, displacement from the origin. All those are position vectors. So in red, these are position vectors. They originate position vectors. And always remember that you have to indicate the direction of a vector, because when we started, we said a vector represents a quantity that has both magnitude and direction. So those are position vector. Now these are column vector. These are position vector. These are column vector. It is a displacement. For example, 1, 2, 3, 4, 5, like that. You give the direction. Those are you can have another vector. They don't start from the origin. That's also another column vector. You can have a column vector here. It doesn't start. So meaning the blue lines represent the blue vectors. These are column vectors. I hope that is clear. Then you have to know how to write. For position vector, for example, this one, if we are to label this 1, 2, 3, 4, 5, 6, 7, 8, we have 1, 2, 3, 4, 5. This is the origin. Also denoted by letter O to represent the origin. Now, in terms of position vector, when we are writing position vector, for example, this point, suppose we say this is point A. Coordinates of A are 2, 4. So the position vector OA is equals to, we write the coordinates in column form, 2, 4. Whenever you are given the coordinates of a point, the position vector of that point, the vector from the origin, is when you write the coordinates in vertical form. But when it comes to column, so this is position vector. When it comes to column vector, you check whether you check the displacement along the x-axis. For example, for this vector here, this one, suppose we label it is PQ. The coordinates of P are 2, 2. And the coordinates of Q are 8, here 8, and 4. So the column vector PQ is equals to, we say it is displacement in x, so we say 8 minus 2 and 4 minus 2. Displacement of x and displacement of y. So this will give us 6 and 2. So the displacement, the component of this vector are that one, that is 6, and that is 6, and that is 2. So I hope now you can differentiate between column vector and position vector. And that brings us to the end. I'll get a question maybe for you to practice on this. But that is a position vector and column vector. So this is an example that you can practice on, or practice question. Let's call it a practice question. So practice question, you find the coordinates of P if OP is equals to OA minus OC. That is equals to, if OP is equals to OA plus OB plus, not plus but minus OC, and the coordinates of point of points A, B, and C are 3, 4. We have minus 3, 4, and minus 3, minus 4, like that, respectively. Write the column vector AB and AC. So you can practice on that, and you'll be able to understand about the difference between column vector and position vector, and I hope that is going to help. So in our next lesson, we are going to deal with the magnitude of, that is magnitude of a vector and the midpoint. Magnitude of a vector and the midpoint, and we end up with translation.